a short presentation on understanding cognitive systems. I'm Jim Sporer, and I'll be presenting today. Today's talk on understanding cognitive systems will cover, first of all, what is a cognitive system entity, and we'll play a little bit with that word entity, both biological cognitive system entities as well as digital cognitive systems entities which depend on artificial intelligence. Then we'll talk about how to build them, understand them, and work with them, and then steps towards the next generation cognitive curriculum dealing with types of digital cognitive systems and types of courses available for learning about next generation cognitive systems. So let's begin by talking about what is a biological cognitive system entity. So as we look at these pictures here, we see ants, wolves, crows, dolphins, monkeys, and people. And in the book, The Symbolic Species by Terence Deacon, subtitled The Coevolution of Language in the Brain, we can understand that all of these different biological cognitive systems, each of the individual entities, individuals have brains, but it's really the interaction of multiple individuals with brains that through some sort of symbol system, in the case of the ants it's a chemical symbol system, but through some sort of symbol system, multiple individuals with brains interacting are able to develop, to learn, and to do more and more sophisticated tasks. So when we think about biological cognitive systems, it's good to have this diversity of examples to think about as we think about brains and learning and symbol systems developing between individuals. But we also have to think about not just the individual, but the group in which an individual becomes an adult in that group, and we also have to think about the species surviving over multiple generations. And of course, this is very different from digital cognitive systems, at least today. And to understand digital cognitive systems, I always like to start with science fiction because those are the extreme examples. And we have an individual smart machine, Commander Data from Star Trek. He's an artificial intelligence entity. But we also have Tony Stark from Iron Man, who is using Jarvis, his AI, in order to have his intelligence augmented. So in addition to, when we think of digital cognitive systems, we don't want to just think about individual AI smart machines like Commander Data. We want to think about the much more, frankly, realistic cases in the short term of intelligence augmentation and how are smart machines going to help make people smarter. And I do want to mention Thomas Friedman's latest book, Thank You for Being Late, An Optimist's Guide to Thriving in the Age of Acceleration, has a chapter on AI versus IA, and I think it's a great book, actually, from many perspectives, but I think he also does a very good job of talking about this distinction between artificial intelligence and intelligent augmentation when it comes to digital cognitive systems. And we'll explore more of the differences between biological cognitive systems and digital cognitive systems later in this talk. So let's think about building a biological cognitive system. In fact, let's think about a person. And it takes about 10 million minutes of experience to go from a baby to an adult in our society. And as we think about, this 10 million minutes of experience to go from a baby to an adult, for the person, a biological cognitive system, there are no digital cognitive systems yet that have all of the capabilities of an adult. And in the book, The Master Algorithm, Pedro Domingos talks about the day that may be coming when we'll be able to build digital cognitive systems similar to the way that we, quote unquote, build biological cognitive systems by having many of them interact through many million minutes of experience to develop capabilities more like biological cognitive systems, but that's not really possible right now. When we think about once you have an adult biological cognitive system, a person, then they begin to specialize. Maybe they become a dancer, maybe they become a pilot, maybe they become a doctor. And going from a novice to an expert, which is the second stage of learning for people in our society, this takes about 2 million minutes of experience. You've heard about 10,000 hour rule of deliberate practice. Well, 10,000 hours of deliberate practice, if you count sleep and other activities, is about 2 million minutes of experience for a person. And again, since we do not have the master algorithm that Pedro Domingos talks about, although he's confident that we're getting close to having a master algorithm, because we don't have the master algorithm, building digital cognitive systems is quite a bit of work, and there's this book, Knowledge Engineering, Building Cognitive Assistance for Evidence-Based Reasoning by George Takeuch, which has just come out, which gives an example of typical ways that people try to build digital cognitive systems today. I guess the short version of this is that it's still a lot of work, and they can be very brittle. So when we think about building digital cognitive systems, though, if you look at the history of artificial intelligence, there's been quite a bit of progress. In 1956 at the Dartmouth conference, when artificial intelligence began as a separate discipline formally, people at this conference said within a few years machines would be smart enough to win the world championship in chess, but you can see that didn't really happen until 1997. Almost a little over 40 years later. So there was a lot of optimism that building these digital cognitive systems was going to be a lot easier than it's turned out to be. It's taken a long time for computers to get fast enough. Building the data sets required to build these systems. In 2011, for example, IBM was able to build Watson to win in Jeopardy. That couldn't have happened without Wikipedia existing. That's 100 million hours of human effort to build Wikipedia. That's one estimate anyway. But we do see through the history of artificial intelligence that the building blocks have been getting better. Many vendors, IBM for example, has the Watson APIs on Bluemix Cloud available. There's also open source efforts like the OpenAI Gym. There's quite a bit of activity now to provide the basic building blocks for digital cognitive systems, learning components, perception components, speech recognition, image recognition. These are all becoming standard building blocks for building digital cognitive systems, and these are available as service offerings from a variety of vendors as well as some open source efforts. So when we think about building biological cognitive systems through many millions of minutes of experience to become an adult and then to become an expert, and digital cognitive systems still in an early stage, really we should be thinking about building socio-technical systems, because these artificial intelligence smart machines have to help people perform tasks within a socio-technical system. The data sets are getting better. ImageNet is now up to 14 million images with over nearly 22,000 sim sets of similar images. WordNet exists. We just talked about Wikipedia. MIT, the Human Speechome Project, has recorded 3 years of the child's language development. So that's a very large data set. More and more, because of smartphones, people are doing life logging. So there's YouTube and very, very large data sets of experience that are being captured. But I do want to emphasize in this book here, Co-Creating Humane and Innovative Organizations, Evolution and the Practice of Socio-Technical System Design, that in building practical digital cognitive systems, it's really about fitting them into socio-technical systems. And in order to understand these biological and digital cognitive systems, there's quite a few lessons that can be learned by comparing, how do we observe biological cognitive systems, how do we observe digital cognitive systems, how predictable and auditable they are. With digital cognitive systems, we hopefully will have much more predictable and auditable cognitive systems than we've had in the past with biological cognitive systems, and that has some differences and advantages. Of course, the hardware is different from brain-based neuron systems to microprocessor-based transistor systems. The software is different, and the machine learning algorithms is different. The disciplines that study these are different, from psychology and cognitive science to design and engineering and computer science. And how we think about data, experience, and transformation for these two types of cognitive systems is different as well. As we think about 2016 and the types of digital cognitive systems that are available now, IBM Watson, Apple Siri, Microsoft Cortana, Google Now, Amazon Echo, Samsung just acquired Viv. Viv was created by the same group that created Siri. Facebook M. We've got driverless cars coming from Tesla and Uber. And of course, SoftBank has Pepper now and Romeo. These are the different types of digital cognitive systems that are making their way into socio-technical systems near you. As we think about a next generation cognitive curriculum, one thing we have to keep in mind is that this is a time of accelerating change. So in 2016, the courses are how do you build a cognitive system for a question answering task. And typically it takes 9 months to build a question answering system that might only be 40% accurate depending on the domain, and 1 to 2 years for 90% accuracy, and that accuracy comes mostly from rejecting questions that are too hard to answer. So you can see that in 2016, the courses on how to build cognitive systems take quite a while and quite a bit of data, even though the building blocks are getting much better. Machine learning is getting, deep learning is getting much better. Data sets are getting larger. Machines are getting faster. But still, it's possible, but it's quite a challenge in 2016. By 2026, though, we project that it'll be possible to ingest a textbook within about a week and have a student-level question answering system almost automatically. So in 2026, the course won't be so much about how to build digital cognitive systems for question answering tasks. The challenges will start shifting to how do you use a cognitive assistant to be a better professional, like a doctor or a lawyer or an accountant or any other type of job. By 2036, the ingesting of a textbook to build a question answering system we project will happen in 1 day, and it'll be a faculty-level question answering system. And then we shift the terminology a bit. The courses will most likely focus on how do you use a cognitive mediator, not a cognitive assistant, but a cognitive mediator, a trusted cognitive mediator to help you build a startup. And these cognitive mediators will have episodic memory, so they'll know a person in some ways better than the person knows themselves. So there will be issues around identity and responsibility that start coming to the fore and will have to be integrated into courses certainly by 2036. And by 2046 and 2056, the courses will shift to how do you manage your workforce of digital workers, because by 2046 it's projected that everybody will have the equivalent of 10 digital workers each, and by 2056, 100 digital workers each will be the norm. So we can see as we're planning to create next generation cognitive curriculums, we have to factor in the increasing capability. At some point, perhaps we do have what Pedro Domingos calls the master algorithm, in which case building digital cognitive systems becomes quite different from what it is today. If we think about today, though, the intelligence building blocks that we have for artificial intelligence systems, learning is making a lot of progress. A lot of deep learning is in the news for perception tasks like image recognition, speech recognition, deep learning is very effective. However, when you get to reasoning, we still don't have systems with common sense reasoning capability. In spite of Doug Lennett's, multi-decade effort with psych, common sense reasoning is still an unsolved problem. And also interactions aren't very natural. So there's still quite a bit of work to be done in applying learning techniques to common sense reasoning and natural interaction across a wide domain of knowledge. And also, even in knowledge systems, we don't really have any systems that truly understand institutions, laws, and can reason about ethically about actions. This is still the forefront of research here. So even though the artificial intelligence component building blocks are getting much better, the knowledge graphs are huge. Every vendor has a chatbot capability. There is reasoning capabilities in many systems as well. Still, these are relatively primitive compared to learning for perception tasks. And as we said, it's not just about building smart machines, it's about building intelligence augmentation, so the science of how people work and the psychology of integrating these systems with people and the design of socio-technical systems, making sure there's some business or societal value that come from the design of these systems. And, it's very interdisciplinary to create socio-technical system design, with the legal issues and the various other issues associated with socio-technical system design. So a next generation cognitive curriculum class will not only have increasingly better artificial intelligence building blocks, but hopefully better templates on the intelligence augmentation side as well. And we can start asking the question of what types of digital cognitive systems do people want? And IBM at the beginning of 2016 had over 250,000 employees who were asked the question, imagine a digital cognitive system to help you do something important in your personal or professional life. And thousands of different projects were identified by IBMers, and those types of digital cognitive systems, we can identify 5 types. There's the tool type, the assistant type, the collaborator type, the coach type, and the mediator type. And taking a look at these, the tool, of course, is the simplest, very specific input-output relationships expected in these digital cognitive systems. An assistant digital cognitive system is a bit different. It deals with the ability to do many different tasks, not just one specific task, and a digital cognitive assistant also understands its limits and how much it can get done in a certain amount of time, so there's a lot of understanding of itself. A collaborator is even more sophisticated, has to have a very sophisticated model of the user and who they're collaborating with. A coach, an even more sophisticated model of the user because the strengths and weaknesses of the user and how to guide them in their development. And a mediator, even more sophisticated because the mediator has to understand laws and institutions and basically how to successfully co-create value between people. So if we take a even more detailed look here at these 5 types of digital cognitive systems, tool, assistant, collaborator, coach, and mediator, we can see that each of the model capability and challenges and relative difficulty levels of these 5 types of digital cognitive systems, they all, of course, have to have an improvement model and some sort of learning and data to help them improve over time. A task model, which requires perception, and there's a great deal of the challenges, the variety in the real world. Some of them also require pretty sophisticated models of self and ability to do reasoning, including common sense reasoning, which is an unsolved problem. And several of them, the collaborator, coach, mediator, also have to have very sophisticated user models, very sophisticated interaction capabilities, and episodic memories. Again, an unsolved problem. And most challenging in the mediator case, the world model isn't just the physical world and knowledge of the physical world, but also a model of laws and trusted relationships. So as we think about next generation cognitive curriculum, building these 5 different types of digital cognitive systems, and building these 5 types of models and capabilities and overcoming the challenges is important. As we look at the courses that exist today, my next slide will talk about some of the AI MOOCs, but there's also from IBM, we have these Watson Innovation courses and various online tools that people can get at, the building blocks. Here are some of the popular AI MOOCs today from top universities. And just in closing, I'd like to give a few comments, some personal reflections on these building blocks getting better. When I was born in Maine in 1956, this was the phone in the farmhouse that I grew up in. It was made of wood. It was a party line phone. When I got to MIT 20 years later, this was the rotary phone that was in my dorm room. When I got to Silicon Valley 20 years later and was working for Apple, this was my first mobile phone. Now I work for IBM. I have a smartphone. But by 2036, whatever I have will have the computing power of one brain, one biological cognitive system person, and by 2056, the equivalent of 100 brains. So in 1972, I wrote my first program on punch cards, and today we at IBM make freely available the Watson APIs to any faculty and student in the world that wants access to them. So by 2036 and 2056, I think we really have to try to imagine not only the building blocks getting better from an artificial intelligence perspective, but the building blocks will be getting better from a socio-technical system design perspective, an augmented intelligence perspective as well. So please do come visit the IBM Almaden Research Center, and we can discuss these topics in more detail. Thank you for your interest in listening to this talk today.